Hello and welcome to Engineering Principles with Mr. Watts. Today I'd like to talk about the Trebuchet simulation that you will need to do before designing and building your trebuchet. At this point you should already be familiar with the parts of a trebuchet. This is a model, a 3D model of a stand like the one you may be using. We have a base, we have supports, we have a pivot point, we've got an arm, and not showing on this trebuchet would be the sling, which consists of a string with some pocket on it and a way to release it. But for today's discussion, we're really going to talk about what happens when we change the design of that trebuchet arm. I've got several different designs that we can bounce between. That one's just a nice rectangle. This one is a low inertia design. This would be a very low center of gravity design. You can make this arm look like anything you want within constraints. The challenge will be to optimize that for best performance. Simulation is about optimizing things to improve performance. Engineers use simulations to help solve complex problems when there's no easy answer. And trebuchets are one of those very complex things. In the olden days, back in the medieval days when trebuchets were a war implement, they would have to build a trebuchet and try it. And if it didn't work like they wanted to, they'd have to modify it and try it again. In the last 20 years, some smart people have come up with mathematical equations that describe how trebuchets work, and so we can now use mathematical models, also known as simulators, to simulate what would happen, and we can do through a lot of iterations very fast to come up with optimal designs. So this lesson is about learning how to use a simulator. There is a simulator that is linked in the assignment in Canvas. It's at virtualtrebuchet.com, and there's also a spreadsheet that I've put together that will help you with your simulation, the simulation results. I'm going to jump to that spreadsheet right now. There we go. When you open this, you will be asked to make a copy, and then I want you to find the tab that says short. It's very important. The design requirements changed from the original when we implemented the short model that we'll be doing this year. In this, there is a link to the starting values for at virtualtrebuchet.com. If you link that, then it will take you to this website right here with those starting values, and you can see that this value, the 2-inch, 2-inch, 8-inch, 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 3.5, they all line up all the way down, or pretty close to all the way down. This is the simulator that's going to run the equations based on this design. And here's a place for us to store the designs that we've tried and keep track of what helps us get better. So just very quickly through this project, first let's jump over to trebuchet.com, and you can see that it asks for the length of the short arm and the length of the long arm. In our design requirements, the total of that can be no longer than 10. I've started with a 4:1 ratio here, which is a pretty good starting point. You may want to verify that. There's the length of the sling. Usually you want to start with the sling length being similar to the long arm length, but again, you may want to vary that. You can play with the length of the weight. The weight hangs from the bottom here. You need to make sure the weight doesn't hit the ground as it drops. The height of the pivot in our designs, I think I've set the pivot height at 9 inches. That's actually plenty high for this kind of design, but there is some possible variation. If I show you this, there are different holes if you want to go shorter than that for the arm. And we jump to my old screen again here. Let's see, let's keep going down here. A uniform arm would be as if we made it just out of a solid log that was the same diameter all the way down. That's not a very optimum way to do it, so I'm going to make sure that you have that unchecked, and you're going to tell it the mass of the arm, the inertia of the arm, and where the center of gravity is. All of those can come from your 3D simulation. For now, I'd like you to just start with the numbers I've given you, and you can tweak those a little bit if you want. The mass of the weight I give you, do not change that. That is the, no, I'm sorry, the mass of the weight you do get to change. In our design requirements, the weight is whatever you can fit legally and safely in a 0.25 liter water bottle. So that's about a cup of water, which weighs half a pound or so. But if you fill it with sand or rocks or gravel or nuts and bolts or coins or something else that you might have around, I've seen students get up to about 3 pounds in those little bottles. So depending on what you want to do. 3 pounds may be too much. I've seen trebuchet arms break or bend, cause problems. So come up with a weight that you think is good. Projectile, you'll be using a 1-inch ABS ball that I 3D print and will give to you, so you don't have to worry about that. Keep its mass the same, and you won't have to worry about the wind speed, but you can tweak the release angle a little bit. Now 45 degrees is usually what you'd consider the optimum release angle for a parabolic, just a projectile flying around, but it's not always the right release angle for a trebuchet, so you might want to play with that. If I feed in all of this data and hit submit down at the bottom of this page, it will actually run through a little exercise where it animates the trebuchet firing, and you can see in this one we got a distance of 19 feet and change, a height of 6.5 feet time. There's some efficiency numbers here that are also interesting to write down. A well-designed trebuchet should be closer to 80 to 90% efficient. So these starting numbers are not optimized. You want to find some maximum numbers, some better designs than this one that should be able to project a ball about 20 feet. All right, so how do you do that? It's kind of complicated. We've got a lot of variables. I'm going to jump over to the spreadsheet now. If you'll focus on this side, we've got all of these things that can vary, but we also have the design constraints. And so look at those comments. The top two should add to 10. If I were to put 3 and 8 for my dimensions of my arm, you can see that adds up to 11, and that is giving me a red highlight. That would be illegal in this design. So if we're going to have 3 inch behind the pivot, we can only have 7 inches in front of the pivot, and now that little warning message went away. Most of everything else you want to keep the same, so maybe an easy thing to do would be to just select all of that. And then I'm going to hit paste values only. There we go. I'm on a Mac. Yours might vary there. So now we could start tweaking these, changing them. I would suggest that you change one variable at a time, not two. Think of 2 variables you might want to optimize, but change one at a time, and then run the simulations until you get some better results. And I'd change them by small amounts. What if we went to 2.5 and 7.5? So I just changed those 2 values. My keyboard's being a little slow here. Still adds up to 10. Go do the same thing over here. I change that to 2.5. This to 7.5. And then I hit submit again. Did that get better or worse? It got better. Okay, interesting. So that tells me that maybe I want to change those some more. What if I went 3 and 8 And rather than copying everything every time, I would just write down the things that change as you go along here after you've done the starting values. So 3 and 8, we hit simulate, submit, and now we're up to 22 feet. Ooh, I forgot to write down the results for that one. 22 feet with the 2.5 and 7. Let me back up. It's important to write things down as you go. Simulate that again. 23.7. Ah, there, that's interesting. So I look and I got better when I went to 2.5. Got better when I went to the 2.5-inch short arm, but it got worse again when I went to the 3-inch. So there's some optimum there that we need to watch out for. And if I took smaller steps, I could maybe find that better peak. Now, once you've optimized it for one variable, that doesn't mean it's optimized. And I'm going to show you a little graphic. This is not of a trebuchet at all. This is something completely unrelated, but it gives the idea. If you had two variables you were playing with, say this was the short arm length and this was the sling length, they actually have this complex surface that defines how they may interact. Let's pretend that when we were just starting, we were playing with maybe we started out right here with an unoptimized design. We'll say right there. And we found that if we went this way a little bit, we got better. And if we went further, we got worse. So if we stop right there and now find another variable to play with, then we can change that variable and watch until it starts getting worse. Now I'm up here near this peak, and I can go back to my first variable and check that, oh, that's getting worse. This would get better. This would get better. This would get better. Just about the same, worse. Okay, this must be the best. Now let's check my other variable. Here, no, here, yes, here, no. Now we found a peak. We've kind of zoomed in on that iteratively, playing with one variable till we find a relative peak, another variable till we find a different peak, another variable, and then back to the first, and you keep zooming in until you follow this ridge up to some peak. Now that may not be the optimum for the whole design. There may be another peak over here somewhere, but at least that gets you in to one. Now if you're changing too many things at once, you won't know which way you're going. So a hint on simulations, take a lot of small steps, write down your results, both the good and the bad. If it gets worse, that's really important because that just told you hit a peak or you were going the wrong direction. It can help point you in a better direction. So hopefully that made sense. If not, watch it again. Come ask me, send me an email. We'll talk you through it. So one or two variables at a time, we found that this wasn't great. Maybe we could come in to 2.25. And that would mean this has to be 7.75. Well, again, let's type those in here. 2.25, 7.75. Go ahead and submit. And we got better yet, 28.6. So I'm glad I checked that intermediate value. That was much better than either of those. This is a good value to hold to. Now let's grab another variable that we can play with. Oh, the mass of the weight. What happens if we got a weight that was a lot heavier? Maybe we got a 2-pound weight. Now let's see what happens. Mass of weight comes up to 2 pounds, and simulate. We went up to 41 feet. So you can see there's a lot of optimization to do. I'm going to let you play with those variables. I think the arm ratios, the sling length, and the center of mass of the arm are all very important. So those are things to think about as you're playing with it. One of the things that you may not understand well at this point in your schooling is inertia. Things that spin or rotate have rotational inertia. It's how hard it is to get it to start turning, and conversely, how hard it is to get it to stop turning. Many of you have been on a bicycle, and you know that if you spin the front tire of a bicycle, it'll spin for a long time if your bicycle's in good shape. And that's because the bicycle wheel is on purpose a very high inertia design. All of the mass is very far from the center. Once you get it moving, it stays moving. This helps you coast, this helps you turn, and makes a bicycle a very efficient way to get around. If, on the other hand, you went down to the pedal on a bicycle and just spun the pedal, you would find that it will turn maybe once or twice and then it will stop. That happens to be a very low inertia design. Most of the mass is right there at the center, just very close to where the rotation happens, at the hub there. And that's also on purpose. You don't want to spend a lot of energy to start and stop the pedals. You want to be able to coast without affecting how much energy the bike loses. And so it's good for pedals to be a low inertia design. I have got a couple of models here. This one is a low center of gravity design. This is 2 inches, that's 8 inches. May not be the optimal, but I put my pivot point here where this hex nut is, and then I put as much of the mass as I could on this side, and I put a very thin tube here. And so in this design, the center of mass is within about 1/10 of an inch of right here. If I were to look at the uniform design, the center of the mass is clear out here. As the weight's trying to pull down, all of the mass of that arm is working against you. So that's one thing you can play with. Another thing that you consider is, what about a low inertia design? In a low inertia design, most of the mass is around the center, and the long pieces are low mass. So this would be a low inertia design. This would be actually a fairly high inertia design with a low center of mass, and the uniform design has a high center of mass distance. And it's a pretty high inertia design because the weight is spread out everywhere. So different things to think of as you're doing your simulations. As you do this in the assignment, I need to have you do at least 10 simulations. I've got 12 columns for pre-designed simulations. Add more as you need to, but eventually you'll come up with an optimum design. What did I do? I forgot to write that one down, didn't I? 41 feet. It's important to keep tabs on this as you go. I increased the mass. The distance went up very quickly. So anyway, do as many simulations as you can, and then highlight, maybe this is the simulation that I like the most. Let's maybe set that in nice and yellow. This is the one we're going to go with. And that gives you a good starting place for your design. So this assignment, you each need to play in the simulator, get the best results you can while still keeping the design buildable, and watching out for any little red things that pop up, or definitely make sure you're staying within the ranges here. I will not give you credit for simulations that are outside of the ranges I've mentioned here. So there we go. Good luck on your simulations. As soon as you've finished your simulation, you'll want to do a sketch of your simulated design, and then the next step will be to model that design in a CAD program, and we'll talk about that in a different video. We'll see you next time.